Hey guys, here we are for chapter 18. We're going to talk about air pollution and ozone depletion. Today, section 18.1, we're going to talk specifically about the atmosphere. But as always, before jumping straight into the atmosphere, let's take a look at a core case study. Today's core case study, Los Angeles. In 1950, Los Angeles had some of the dirtiest air in the world. Now, Los Angeles has mountains really on three sides of it. And with the industry and the automobiles putting out pollution, there were hardly any checks and balances of trying to clean it up. It would just get trapped in this kind of bowl. Once again, some of the dirtiest air in the world at that point in time. Public protests started getting so bad in the 50s and early 60s, people would put on gas masks to go places. Some of it was protests, some of it was just the air was so bad. People kept their kids home from school on some of the worst days. Protests going on all over the area that they had to do something to clean up the air. By 1970, Congress had passed the Clean Air Act. In 1969, the government actually took the automobile industry to court over the fact of how they had delayed putting in catalytic converters and doing anything to clean up the pollution coming out of the cars. Literally, the United States government was suing the car companies because there were things they could do, but they were dragging their feet and purposely delaying it, putting off doing it because it would cost money and it would cut into their profits. But once again, 1970, we passed the Clean Air Act. This mandated certain pollution control measures on industry and automobiles by and large. It has made dramatic improvements in LA. Now the picture we have back here, LA still has its bad days. But even though the number of cars have practically tripled in LA, industry has gone up, the population is greater, their air quality is 70% better today, 70 years later, than it was in 1950. We've come a long ways, we just have a long way yet to go, especially in some cities. A lot of areas are much, much better. The fine particle pollution has been cut in half since 2000 even. So in the past 20 years, we've seen just marked change in what we can do. And this is what we're after. What can we do, especially as we move to more renewable resources, we're not using as much fossil fuels, these numbers will get even better. All right, 18.1. The atmosphere. Now, in reality, we're really going to talk about the innermost layers of the atmosphere. 5 layers, really, we kind of talk about the first 4, but today's lecture, we're only going to talk about the first 2. The troposphere, this is where all the weather happens and really what supports life by and large on the planet, and the stratosphere, which contains our protective ozone layer. Those are the 2 we're going to focus on. Now, when we talk about the atmosphere, we're just talking about the thin blanket of gases that surround the planet. You think about an apple, right? Well, the skin of the apple, that would represent the atmosphere. It's actually a really teeny tiny thin layer. Picture I have of the Earth back here, that kind of little blue fuzzy haze, that's our atmosphere. Very, very thin thing that protects us from outer space, if you will. Now we're going to talk about a few different terms. Density is one of them. Density, mass over volume, right? The amount of matter packed into volume or space. The more matter packed in, the denser it is. Now the closer you get to the planet Earth, the denser our atmosphere is. The higher up you get, the particles are spread out, less dense, right? Once again, density, just a matter of mass over volume. How many molecules are packed in? So, the closer we get to the Earth, the denser it is. The higher we get, density decreases. We're also going to talk about pressure. There's atmospheric pressure. This is the force per unit area of a column of air. Literally, how many air molecules are hitting, impacting me every second, if you will. There's a whole big column of air pushing down on top of me, and this is our atmospheric pressure. Just like underwater, the deeper you go underwater in a pool or a lake, you feel the pressure. The water is pushing down. The same thing happens with atmosphere. Obviously, water molecules are much denser than air molecules, so the pressure doesn't feel as great, but it's still there. Once again, even though our density decreases with higher altitude, well, atmospheric pressure also decreases with higher altitude. So density and pressure very closely related. Let's take a look at the picture we have back here. This is showing the different layers. We start at the very bottom, we have the troposphere, followed by the stratosphere, followed by the mesosphere, and then by the thermosphere. Beyond that is what we refer to as the exosphere. Well, let's start off. You've got a couple of different lines there. Well, it's kind of gradiated, right? It kind of starts off at light blue, moves up towards really dark blue, and then we've got some little white lines. We've got a red squiggly line and a black line. Well, let's address these. First off, just the different layers. The troposphere, this is where weather is. This is where most of our water vapor, clouds, all that stuff is occurring. Right above that, we have the stratosphere. That orangey layer, that's the ozone layer. It's right at the bottom of the stratosphere. You know, tippy top of the troposphere, bottom of the stratosphere, where we find the ozone layer. Above that is the mesosphere, the thermosphere, and we get into our exosphere, really kind of moving into outer space. Very, very few air particles whatsoever. Now let's address the black line, kind of the easiest. This is pressure, atmospheric pressure. The greater pressure, the farther we're going to the right of that column, is greater pressure. So down at the troposphere, we have highest pressure. As we go up, the pressure gets less and less. Very minimal pressure. Now let's look at the red line. The way we identify that we have moved from the troposphere into the stratosphere is not a hard line. It's not that we say 17 kilometers up, troposphere, 38 kilometers up. No, it's based on something else. It's based on a temperature change, because the height of the troposphere can change depending on where on the planet you are. It's a little higher at the equator, it's a little shorter at the poles, based on where you're at in high and low pressure systems. So how do we know we've moved from the troposphere into the stratosphere? Temperature changes. In the troposphere, that red line, the higher up we go in the troposphere, the temperature decreases. It gets colder, colder, like we go up a mountain, right? You go up a mountain, colder, 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 colder. Well, you go up an airplane, colder, colder, colder. Let's take it to a weather balloon. Weather balloon's going up, we got a thermometer in it. The higher it gets colder, 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 until we hit the stratosphere. We start picking up all this ozone, right? And it's picking up. You hit the stratosphere, now the higher you go, it starts to get warmer. It starts to get warmer, 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 until we hit the mesosphere. When we hit the mesosphere, it gets colder, 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 until we hit the thermosphere. And in the thermosphere, it gets hotter, 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 off into the exosphere, and then we're just into direct radiation from the sun. So these are what those lines mean, what the color coding is, and what we do. But that's how we know the difference between the different layers. Troposphere, colder, colder. Stratosphere, warmer, warmer. Mesosphere, colder, colder. Then into the thermosphere, warmer, warmer. So how we know what the different layers are and the lines between it. Now in the troposphere, when we talk about the troposphere, 75 to 80% of all of the Earth's air mass is in that first little layer, and it's even the shortest of all the layers. It is the closest to the Earth's surface, the densest, and the most atmospheric pressure. Now let's talk about the composition of gases. We've addressed this before. Can you do it? 78% is nitrogen, 21% oxygen, and that accounts for 99% of it. The rest of it, about 93%, is argon, leaving you with a teeny tiny fraction, and that's going to be our carbon dioxide. Now I'm going to use a figure of 0.04, somewhere between 0.04 and 0.03, depends on the time of year, where you're at. Lots of things affect our carbon dioxide levels. Then you have everything else, right? Very, very small amount. Now those numbers don't really account for water vapor. Water vapor is our greatest greenhouse gas, but it varies wildly. You're over a desert, it can be 0%, no humidity whatsoever. Here in Florida, a lot of times, like on a given day, it can be quite hot. But water vapor ranges anywhere from 0 to about 4%. So, you know, the numbers don't always work out when we toss water vapor in, but water vapor is there and it changes a lot. But somewhere between 0 and 4% is water vapor, so that's kicking into how much oxygen and everything else. All right. 78% nitrogen, about 21% oxygen, once again depends on where you are, 0.93 argon. Then we go into our trace gases, of which carbon dioxide is kind of the biggest one after that. But the most important greenhouse gas, water vapor. All right. Now, the rising and falling air currents and greenhouse gases all play major roles in our weather and our climate. We've looked at a lot of these things from different avenues when we talk about climate and weather. After the troposphere, we kick into the stratosphere, right above it. Now, this is going to be somewhere between 17 kilometers and 48 kilometers up. Once again, it depends on a lot of factors. Air currents, pressure, are we near the equator or near the poles? But very similar composition to the troposphere when we're talking about gases, except much lower volume of water vapor. We have a much higher concentration of ozone. Teeny tiny trace amounts of ozone at the troposphere, but in the stratosphere, much higher levels. O2, because of the UV rays, is getting converted into O3, making up our ozone layer. Now, our ozone layer is filtering out 95% of the harmful UV radiation. It is our worldwide sunscreen. It's what allows me to go outside and not get sunburn immediately. I got about a 15, maybe 20-minute window in the Florida sun before I start to get sunburn. Thank goodness for sunscreen. But the ozone is our worldwide sunscreen. Too much UV radiation can kill plankton, no bottom of the food chain, disrupts everything else. It can kill lizards, you name it. We have to have it. It is what allows life to exist on this planet as we know it. Well, guys, that's pretty much it for the lower layers of the atmosphere, which is really all that we truly interact with on a daily basis. Troposphere, stratosphere wraps us up for today. Next time, come back and join me and we will talk about outdoor air pollution.